I'm Ivanka, a high school student from Minnesota, and I'm really passionate about climate and sustainability. So I did a research project at the U of M for the past 3 years under Dr. Joel Heuschli, and then I also did a project at Cornell, and both of them were in reducing methane emissions from livestock using feed additives. So that's when I first got interested in methane emissions. So then I started this initiative, MethaneMatters, to educate people on methane emissions, sources, impact, and some mitigation strategies. So I make these videos and the podcasts. And then I also wrote this book on methane emissions that goes a lot more into detail than any of my videos. Yeah, I'm really excited to hear about your interesting work in a different aspect of climate.
Great. So I'm Ben Zaitchik. I am a climate scientist, hydrologist, and kind of working in the interface of basic science of the Earth system and applications to human well-being. I'm at Johns Hopkins University, where I'm the chair of the Department of Earth and Planetary Sciences, doing work both locally in Baltimore, working a lot with communities on various climate resilience issues, and also globally, working on the interface between weather and climate and our ability to predict weather and climate and outcomes such as infectious disease, food security, infrastructure resilience, and other elements for which we try to develop early warning systems that can best inform adaptation decision-making.
Okay. Wow, that's really cool. So what's kind of like your educational background and how did you get started?
Sure. So climate science and the earth sciences in general are very interdisciplinary, and I think a lot of people find them a little bit later in their careers, right? You come through high school and it's like there's biology, chemistry, and physics, and then some of these other fields you find out about later on. So I did my undergraduate degree in biology, did undergraduate research, actually in molecular biology of plant genetics, and then got interested in ecology and thought, oh, the genetic stuff is fascinating, but I want to understand the system. And so then I did a little time after I graduated, doing some research. I lived in the Middle East for a while, looking at desert ecosystems. And then from there, I went back to Seattle to get my master's in kind of crop and soil science, understanding in agricultural systems, how soil and water and meteorology kind of combine to influence outcomes. And then after that, that was useful because my master's thesis, I got the opportunity to work on some hurricane studies. It was post-hurricane Mitch, which hit Honduras and other parts of Central America. And in 1998, and I was able to go down there a year or two after that and work on Hurricane Mitch reconstruction, understand some of the impacts and strategies for building back in a more resilient fashion. They got me interested in the climate system, and then I ended up doing my PhD, where I was again intending to kind of look at that kind of on the ground soil, crop, vegetation, adaptation systems. But the PhD project that I was planning to do was in the Middle East again. And this was kind of in Syria near the Iraq border. And I happened to start my PhD in September 2001 when 9/11 happened. And that immediately made it a little difficult to do that kind of field work. So I ended up kind of pivoting into understanding the climate system more broadly. Ended up doing my PhD really in the realm of atmospheric modeling and remote sensing, which at the time was just a necessity because I couldn't really get to the field, but ended up being really fascinating stuff. And so then I ended up going to NASA as a research scientist after graduating with my PhD, and then one thing leads to the next, but was able to kind of look at the satellite tools and the numerical modeling tools to understand these systems.
Okay, wow. So what kind of projects are you doing currently?
So right now, we're doing a whole bunch of work here in Baltimore, where we work with communities on co-designing climate resilience strategies. And so what that basically means is, urban climate is scientifically fascinating. It's really complex. We build these urban systems and urban landscapes, and really don't understand what the implications are going to be for the environment that we live in. And so we have a scientific interest in understanding that, how the urban heat island operates, how different kind of precipitation and urban flooding patterns evolve. But we want those questions to be guided by the needs of different stakeholders. So those can be community groups. In particular, in Baltimore, we focus on some of the neighborhoods that are disinvested and have high vulnerability. But also the utility company and the city government and the state government are all interested in trying to understand how extreme weather events are playing out and possibly changing under climate change, and how that then interacts with the infrastructure of the city to influence outcomes of interest. And those outcomes include things like extreme heat, air pollution, flooding. These are things that people ask us about. So we would design this stuff in collaboration with them. So we do a lot of work there, and then we also continue to work internationally a lot, well, nationally and internationally. Nationally in the U.S., we look at things like droughts. We got some projects on what they call flash droughts, rapidly evolving droughts that seem like they might be becoming more common under climate change, and then continuing to work in Latin America on climate-informed infectious disease early warning, and in parts of sub-Saharan Africa and South Asia on various water resource questions related to kind of seasonal forecasting of droughts and the impacts that have. So those are some of the things we've got going on, but all in that area of understand the climate system to inform better decision making.
Okay. So what kinds of solutions are you looking at?
Yeah, and so early warning systems themselves are a form of solution, right? So with or without climate change, but especially with climate change, where you're going to have these kinds of extreme events happening. Ideally, we would like to just stop those from happening, but you can't. And again, even without climate change, there's always going to be extreme weather events.
Mm-hmm.
And so if you can have an early warning of something like a particular disease spike, well, then you can get out information to communities, preventative measures, you can pre-position supplies. In some cases, if it's vector-borne disease, maybe you have targeted spraying campaigns, other controls of the vectors. So that's stuff that we would definitely work on in the early warning space. When it comes to droughts, sometimes you're getting ahead of that in order to say, well, is there anything we can do in terms of water management, right, or crop management that can help avoid the impact of the drought? Often you can't stop it, but then what you're really trying to do is inform, again, decisions. For example, like the famine early warning system we work with, trying to say, okay, well, where should we be ready to get food aid, and where should we be ready with humanitarian assistance? So those kinds of solutions we look at. Then longer term, like when you're looking at a place like a city like Baltimore, we're saying, okay, well, what's going to happen with this housing stock, and what's going to happen with this various infrastructure systems we have as the climate changes, and can we, for example, combat the urban heat island by having cool pavements, by having more street trees, all of these things? What are the benefits to energy bills? What are the benefits to health outcomes if we do that? And by doing that analysis now, we can help the city decide where to invest in that kind of longer term resilience strategy.
Okay. So do you also help finally implement these solutions, or just do the research on them?
So I sit at the university, so we're mostly doing research, quite frankly.
Okay.
Like we're trying to inform that, but that's where the partnerships are so handy. So just earlier today, I was talking to some contractors and neighborhood groups that are doing the implementation, and we say, okay, well, how can we use the knowledge that we've developed with research to inform what you're doing, and also how can the evidence basis that we have acquired through our research help justify the investments that you're making, perhaps in building in a way that is different, maybe even a little more expensive up front, in order to make something more environmentally sustainable and make it more conducive to environmental resilience under climate change. And they want to do that, and then maybe we can help in a way that convinces a policymaker to make some incentive structures to encourage that kind of development, or can in other ways affect the economics of that investment that those private sector actors are making.
Okay. So who all do you work with? Like what kinds of people, I guess?
Everybody, and that's what's cool. One thing that's cool about this field, right? It affects everyone. So, we've worked. I mean, again, and being able to work all over the world is a real privilege. So, we've worked with smallholder agriculturalist farmers in East Africa quite a bit to understand from them what their needs are, kind of weather information, and for other kinds of inputs to their agriculture. And then in that context, also working though with national ministries of agriculture and development in places like Ethiopia and Kenya. Like we've done a bunch of work there. Water resources ministries, places like Peru. So those kind of government actors are interested. But then also like community groups in the United States. I often say some of the most fascinating cultural experience I've had have been doing things like working with community groups in rural Alabama and understanding how in my own country, like I can understand the different contexts and circumstances people have when it comes to contending with extreme weather. Work with church groups a lot and other faith-based organizations because they can be really important networking communities. Yeah, utilities, local governments, you name it. Pretty much everybody's got a reason to think about these problems.
Yeah, that's really cool. So who all is part of your team and like your lab composition if you have a lab?
Yeah, we do. We call it a lab. We do a little bit of kind of like wet laboratory work, but not much. Like we're mostly doing numerical modeling, field work. We'll go out and take measurements, and then use of satellite data, right? Is kind of where we're at. So I sit at a university, right? And so most of my folks are graduate students, working for their PhDs, or postdoctoral fellows and researchers who are, or research scientists who have received their PhDs already, and then undergraduates who want to get involved in research in the group. So it's very much kind of students and trainees. But then we also, make an effort to, since we do so much co-development, like sometimes we directly employ people who are, actually working in the community, trying to do urban greening efforts. For example, we've got one person right now who's, got a position with my group because that's the best way for us to ensure that we have tight communication as they do their work.
Okay, wow. So are they mostly from similar like climate backgrounds, or do they come from all over the place?
Yeah, it's a range. It's a really good question, right? So again, because the earth sciences are something that people sometimes come to a little bit later, you end up with some people who are coming just with a math or computer science or a physics background, like the people who come with a quantitative knowledge and want to apply it through the earth sciences. But then because we do a lot of work on health impacts, we have some people who are public health backgrounds and come to it that way. And then you have people who are coming in from various elements of what you might expect. People who maybe were already studying soils or agriculture or atmospheric science as well. So, I think that for people looking to get to the field, establishing kind of some ability to do quantitative analysis is important, but the specific field, you can come from any direction.
Okay, that's nice. So what kinds of technologies do you use in your work?
So we use a lot of different technologies. I would say that space-based remote sensing is big for us. So we use a lot of satellite-derived data. So those technologies are really important. And then you end up pairing that with similar technologies on the ground. So then maybe you have a field measurement of spectral properties or thermal emissions, right? Or around,
Can you
or you
explain
might
what those are?
Well, yeah, sure. So satellite data, right? Almost all satellite data is generated by acquiring signals by basically measuring electromagnetic radiation, right? So light of different wavelengths. So satellites record those data, and from that you might then try to get information. So okay, what does that mean about vegetation, or what does that mean about build properties of the city, right? Or what does that mean about rainfall? And to do that, you then have to kind of connect that to the actual property of interest that you want to understand. So if you want to say, oh, this satellite measurement is telling me about temperature, for example, well, then I also might need some measurements of temperature on the ground. And that can mean measuring the air temperature. It can also mean using instruments that will measure the radiation, the electromagnetic radiation that is indicative of temperature, right? So that you can then connect that to what the satellite's doing.
Okay. Do you use any other technologies?
Yeah, so I mean, a lot of what we do is computing technology, so kind of almost generic, like high performance computing, which we then use both for running physics-based models. So that's basically fluid dynamics, so solving the equations of motion in a way that allow you to predict what's going to happen in the atmosphere, for example. But also, like everyone these days, we're trying to harness the power of machine learning and artificial intelligence. And so that's another kind of different type of high performance computing, when you're trying to kind of train machine learning models to predict things really in a statistical sense rather than by reproducing physics equations.
Okay. What kinds of things do you use them to predict?
So it's a range. So sometimes we're using them to predict elements of the physical system, right? So there are some elements of just even simple weather, right, that we might take for granted and say, oh, we can predict these things with the weather forecasts. When you actually look at what's happening in these models, we can't resolve every raindrop, right? You're not really simulating that. Instead, we're doing this kind of on a coarse scale and an average scale. And we use these things called parameterizations to try to convert some, kind of let's say at 1 kilometer, like a mile resolution, like how much humidity is there and what's the temperature and where's the wind blowing. And we want to convert that into how much rain. you might parameterize that. We can then use machine learning to try to learn those patterns and train that in a way that then is able to predict what's happening locally based on this kind of broader understanding of what's happening physically. So that's one way we use it. We also use, like, again, the machine learning approaches to say, okay, we do all that analysis. We bring in the satellite data, we bring in the models, we bring in the observations we've taken in the field of weather, climate, water, ecology, but then we want to predict malaria risk, right? Or we want to predict what the crop yields are going to be 3 months from now. And so then for those kinds of approaches, we will also kind of employ these kinds of machine learning techniques.
Okay. Oh, that's a lot of stuff. So what kind of challenges do you face in your work?
I mean, some of it's good challenge, right? It's like, this stuff is fascinating because it's not easy, right? I mean, like, doing this stuff, like, it's what makes science great, right? Like, I sometimes say this, I do really believe that science is the most radically hopeful thing that human beings do, right? This idea that somehow we're going to try to, like, take some measurements and use our brains and figure out the world around us, right, is kind of shockingly amazing. And so, and it's not easy, right? And so, like, that's fun challenge, right? It's like, okay, this is a big, hairy, messy, difficult problem. The data are imperfect and they're huge. Like, the satellite data, you're wrangling massive data sets, but you're trying to understand what they mean. And you're then trying to, like, predict the future, right, of something. So I think that, like, that can be really hard, kind of turning data into information and turning information into knowledge in a scientific sense to really test a hypothesis. That's what makes science great, right? Trying to do that. So those are the good challenges. And then, you know, other challenges are like, right, like running a lab is like running a small business, right? And so, like, you know, you need to, if you're going to have students, you got to pay students, right? You got to keep people employed. You got to buy certain equipment and things like that. And so the challenge of kind of, you know, running that kind of an operation, I think, is also kind of a fun challenge, but it's very different from the science itself.
Yeah, I definitely saw some of those during my research too.
Yeah.
What else? Oh, what would you say is the most fun part of your research that you do?
Most fun. Science is really social. I mean, maybe it's not true for everybody. I mean, there are theoreticians probably who, like, do their best work sitting alone in a dark room, right? But for the kind of stuff that I do, I mean, just the fact, and you asked me about who we work with, right? Like, talking to all those people, and then even more so than coming back with your students and, like, trying to, like, work this through. And the scientific workforce is so diverse, right? And so, like, I just take it for granted that, like, I work with people from all over the world, both people who are located all over the world. I'm on Zoom calls with India all the time, right? But also, like, just the people in my group are from all over the world, right? And or from different communities in the United States. And so, like, it's really fun to be able to, like, be working in a group like that to solve a common problem. And so I guess that's it. Like, the most fun part of it is kind of like team problem solving. You know, it's like, and I think that people like that in general, right? Like, it's like you're in an escape room or something, right? It's like that's what you're trying to do here, right? And so I think it's like the puzzle of it is a lot of fun.
Yeah, that does sound fun. So my last question is, what advice would you give me or another high school student who wants to go into a similar field?
Yeah, I mean, everyone has their own path and everyone's different, right? So it's hard to, like, give advice. But I would say, to the extent possible, like, relax. And I don't mean that, and that doesn't mean, like, don't work hard. Yeah, you're going to work hard, right? But do so in a way that you're motivated. Like, let your kind of, you know, let your passions lead you with strategy, right? So it's like, oh, you're really interested in something, great, and also know that, well, maybe that means, you know, shoring up your math skills a little bit, even if you're not passionate about that, right? So, like, you want to be able to, you know, make sure that you're, like, understanding what you're doing as you do it, right? But what that thing you're doing is probably doesn't matter so much, right? It's like you can meander your way into different fields, and just as long as you're, like, you know, rigorous in your thinking and doing stuff that you find interesting, you don't necessarily have to say, like, oh, I need to do X, Y, and Z because I know that I want to be here by this time point. Now, some people are different, so some people will want that. In our field, I would say that, like, it's certainly not necessary. And I get that's different, like people who are going to want to get to med school at a certain time, like they've got a different kind of, set of incentives and structures. But if what you want to do is get into research science, then I think like following your curiosity is really probably the most important thing.
Yeah, thanks. I'll keep that in mind. Okay. Is there anything else you would like to share?
I'm good if you're good. Yeah.
Okay. Yeah, it was super fun talking to you. I definitely learned a lot.
Yeah. Well, congratulations on all you're doing. Great to see you getting involved in these questions early on in your career.
Yeah, I'm super excited. Yeah, it was great talking to you. Have a great day.
All right. Take care. Bye.
Bye.